The last type of functional gauge that we'll look at is a functional gauge for patterns, and then we'll examine the potential for errors contributed by the gauges. When we look at a design specification for a pattern, specifically we're looking, if you recall, for the pattern locating tolerance zone, which is the top component of the composite tolerance frame here, and then the feature locating tolerance zone, which corresponds to the lower component of that composite tolerance. Now, the intent, of course, is to control the position of the four-hole pattern here. So we need to be able to construct a functional gauge that will allow us to check the pattern. So right off the bat, we should recognize that we will need two separate gauges, and that's because we have two different datum reference frames. So whenever your datum reference frames change, your gauges will be different, and in addition, we note that the size of the tolerance zone is different. Now, the same rules still apply as we've mentioned before, and that is whenever you're dealing with a feature of size, you are going to have a maximum material condition here. Otherwise, you won't be able to create this functional gauge, as we'll see. So if we look at the pattern locating tolerance zone first, what we need to do is include our datum reference frame clearly in order to locate the pattern. And then we need to create our virtual condition surface, as we've done with our previous functional gauges. To do that, we start with the MMC dimension for the features, in other words, the four holes, and we note that that MMC dimension is 1.5. And then we are going to add the tolerance zone if it is a solid feature, a protrusion, or conversely, we're going to subtract it if it's an internal feature, which it is in this case, and therefore the width of the tolerance zone, 0.02, that we identified here, along with our maximum material condition, are used to determine the actual diameter of the pins that we'll need to place in the fixture. So here's the diameter for our pins. And then the question is, where are they located? So if we look at our fixture, we are going to need something to identify datum B, and datum B, of course, is this outside cylindrical surface, and then we need to establish as well datum A, and A comes before B, as we can see here. So what we'll need is a locating plate, or three locators, as you can see here, to establish datum A. And then we're going to need something to constrain the location of the feature corresponding to datum B. And of course, that inside diameter should be 8.1, which corresponds to the MMC condition for B. And now what we'll do is we'll place our part inside of that and make first contact with the surface corresponding to datum A, and then of course it should still fit within B. I'll have 4 pins here, and these 4 pins will have a diameter of 1.48. So if the part fits, then we're going to say it satisfies the pattern locating tolerance zone. Now, what about the feature locating tolerance zone? Well, we place, for the pattern locating tolerance zone, we placed our part inside of our pattern locating tolerance zone gauge, and if it passes that, then we're going to want to check our feature locating tolerance zone. In order to check the feature locating tolerance zone, let's go back to the design spec here. We note that we have a width of 0.01, and it's also based on maximum material condition, so that means it will be feasible. And then we are only concerned about datum A. So we're not concerned about where this pattern of 4 holes is located. We're concerned about where they're located with respect to each other. Now, for the feature locating tolerance zone, it's going to be a lot simpler because we only have one datum reference frame, and as you can see here, that corresponds to datum A. So for datum A, we are going to construct a plane, and from that plane we're going to place a set of pins perpendicular to datum A, of course, and they will be located with respect to each other in terms of being on that circle, and also separated from each other by our basic dimension of 90 degrees. Now the diameter of the pins is going to be different, and that is indicated by, again, our MMC for the feature, which is 1.5, and then the width of our tolerance zone, we subtract that in order to obtain the virtual condition, and now we have a diameter of 1.49. So we have 4 pins that correspond to the 4-hole pattern, and as you can see, the outer circumference, which corresponds to B, has no role in this location of the tolerance zones. And so this 4-hole pattern can vary. Again, it's a tighter tolerance than we saw for the pattern locating tolerance zone, but we're more concerned about the features related to each other. So we've seen the role of MMC in functional gauging and how that's an important criteria to determine whether or not you can create a functional gauge based upon a position tolerance or perhaps an orientation tolerance. And then the importance of a virtual condition envelope, so you need to understand how to construct that based upon the type of feature that you have. Of course, whenever you're dealing with a position tolerance, you always have to go back to the true position related to the feature. In summary, make sure that your datum order in the datum reference frame is preserved. So you have to make sure your primary datum, or I should say the part of the gauge associated with the primary datum, makes contact first, then the secondary, and then the tertiary. The gauge features that you create, the pins as we just did in the previous example, have to be located at true position with respect to the datum reference frame. So that will require basic dimensions, as you well know. And then finally, composite tolerances for patterns are going to require separate gauges, and that was clear from the example. Both the diameter of the pins and the datum reference frame are different and therefore require multiple gauges. Well, now that we know how to use a functional gauge and create a functional gauge, as well as the go-no-go gauges, let's think about the errors that might be contributed by the gauges themselves. Of course, there are a lot of possibilities for error contributions, and that's the subject of many gauge R&R studies. But specifically, we want to look at the contribution to the errors because of the gauge dimensions. So what are the sources of error whenever you're measuring something, you're concerned about that? And then how can these errors occur when we're using gauging such as we've described? What are the impact of these errors on your manufacturing system? You should be concerned about that. So let's talk about errors with gauging. Specifically, we'll talk about it with respect to hard gauging, but in our next look at soft gauging, this will also be applicable. Well, when we think about errors with gauging, we think about type 1 and type 2 errors. Now, if that term isn't fresh in your minds, you might want to go back and review that back from your statistics class. Essentially, what we're saying with a type 1 error is, based upon our inspection, we're going to reject a part that is actually good. By good, we mean in terms of the design spec. And we're measuring some type of feature attribute where we saw with our process capability, it will have some distribution, and of course it appears to be a random number. When I look at the type 1 error, rejecting a good part, that part now becomes scrap. So that figures into your calculation of S in terms of scrap rate. Well, if that scrap cannot be reworked, or if we do rework, it has a direct impact on manufacturing cost. First of all, if that enters the waste stream, then everything we've invested up to that point in time will be lost. Or if we have to do additional rework, that will cost additional funds. And so we see a direct correlation between an error here and our manufacturing costs. The type 2 error is different in that we're going to accept a bad part. So if my gauge tells me that the part is good, however, in fact, it does not meet our design specification, then the cost is a little different. because we passed this part, that means problems could come up later on, as we've seen in assembly, because of the relationship that's been defined by the design specification has not been fulfilled in this process. And it can also manifest itself once it's in the hands of the customer in terms of a reliability cost, which could mean recalls and replacement and warranty issues. So the question here is, which is worse, a type 1 or type 2 error? And I'll let you think about that as we go through this. Again, how could this happen with our gauge, which has been specified based on MMC, at least for the go, no-go gauge that we'll be looking at, and LMC. And these are directly tied to our design spec. So how could an error occur even though we've specified the correct gauging? Well, if we look at one feature and we assume that for right now, let's say our process fit variation is equivalent to the design specification in terms of tolerance. So we know from before that here is the design spec and here is the component due to our process. And so, of course, sigma is going to be equal to our range in terms of dimensional tolerances divided by 6. Now, under those conditions, you should be able to answer the question, what is the CP value for this process? Some major causes of error would be, first of all, someone selects an incorrect gauge. And so that's just a human error where the improper gauge was used. Or a neglecting of inspection, and therefore a part could be passed through without being checked. We've already talked about how we use gauges, and so if it's not used properly, you may come away with the wrong conclusion. And then finally, deviations in gauges can occur, especially if I have tight tolerances and there are temperature fluctuations, and the parts can vary in terms of their dimensions because of those temperature fluctuations. That can be a major contribution. If we look at these are major causes of error, but they're not the only causes. So let's look at a type 1 and type 2 error. As you recall, we said the part is good, and what we mean by that is it meets the design spec. However, it's being rejected. And type 2 is actually a bad part. It's outside the dimensional tolerances. However, based on our inspection, we accept it. So here I've drawn the LMC condition and the MMC condition. Now it doesn't matter whether it's a hole or a shaft, a protrusion or an internal feature. What we're looking at is just the range according to our dimensional tolerance. And then this is what we're expecting in terms of our product feature that will vary as a result of the process. Now, if we look at gauge deviations, we're talking about the gauge itself deviating from MMC and LMC. So gauges aren't perfect, just like our part is imperfect, and they have tolerances, which are typically on the order of 10% of the part feature tolerance. However, they will deviate just as we see our part feature deviating. So these deviations are contributing to the area. If our part feature is a shaft, an external feature, then we're going to use a ring gauge, which represents a hole. And what happens when the no-go gauge diameter is increasing? In other words, it's greater than the LMC of the shaft. Well, when that happens, of course, as you can see here, I've moved this red line to the right, indicating that the gauge diameter is increasing. And the rule for no-go was that if the diameter of our gauge increases, then it's more likely we will reject the part. Because again, the rule is if the shaft in this case inserts into the hole, then we're going to say the part is no good. When in fact, as we see here, it's located at LMC. However, because of this increase in diameter, we're offset, and this red region here represents the probability, based on the normal distribution, that we will reject a good part that is at the LMC dimension. If we look at the opposite case, the go gauge, and if its diameter decreases, it gets smaller, then it's more likely that we will not be able to insert a component that is at MMC or between MMC and this actual diameter. And that is our inspection rule, it has to insert successfully. So we're going to reject a part in this red region, and that is the probability of rejecting a part with the go gauge. So you see we have probabilities here associated with making type 1 and type 2 errors. Recall that this is still a good part and this is still a good part. So by creating that type 1 error, we've created a loss in our value because we are rejecting that part. For the opposite, where the part features a hole, it's the same type of situation, only it's reversed in terms of the gauge diameter is decreasing for the no-go gauge, as you can see here, the shaft. And for the go gauge, the gauge diameter increases, so it gets larger. Obviously, we will not be able to fit it into the hole feature. And so again, we will reject a good part. And again, we have a region here that describes the probability of a type 1 error. For the type 2 error, the part feature, if it is a shaft here, again, an external feature, then the gauges are going to be our ring gauges, which are holes, and if our no-go gauge gets smaller than the LMC dimension, then what's going to happen is the gauge diameter is decreasing, and as a result of decreasing, we will not be able to fit a component in this range here into that hole, and as a result, what we'll do is we'll accept a bad part. Conversely, for the go gauge, the gauge diameter is increasing. As you can see here, the hole gets larger, and so all these parts that are outside the spec, they're going to fit into that hole. Remember, a type 2 error, we accept a bad part. Well, the same thing if the part features a hole, only now it's reversed in terms of the gauge diameter because the gauges are pins. And so if the gauge diameter is going to increase, in other words, we get larger because we're approaching a value greater than the LMC condition for the hole, then you can see what's going to happen. We won't be able to fit that pin into the hole, and so we would say it passes the no-go test. Conversely, the gauge diameter is decreasing. It's getting smaller as we move outside the specification range, and therefore we can easily insert that into holes in this region up to that diameter. And those are out of spec, therefore we're also accepting bad parts in both areas. Note the red zone under the probability distribution for both type 1 and type 2 errors. The type 1 error was on the inside of the dimensional tolerance range, the type 2 errors on the outside. Well, let's go back to that question of which is worst, a type 1 or type 2 error. Well, the type 2 error is more uncertain because of reliability issues, so you might be have greater concerns over that. The nice thing is, if we look at our distribution, the probability based upon the gauge error here is a lot less for a type 2 error than a type 1 error. So if a type 2 error is of more concern, which traditionally it would be, the nice thing, it's consistent with the type of error that we're generating, and it has much lower probability. Of course, how do you reduce your type 1 and type 2 errors? The only way to reduce that is to decrease the tolerance on your gauge specification. Of course, as you do that, the cost of your gauging goes up, but your corresponding manufacturing costs and type 2 error costs are going to decrease, so it could have definite benefits. Well, these gauge errors don't happen all alone, but there's some cumulative effect because we're checking multiple part features based on different gauges, and they all have tolerances. So if I look at my x-axis here, what I'm looking at are the number of features that we are going to inspect. And if we're not going to have any errors, then we have to think about what's the probability of no error for each individual feature. Once I have that, and I subtract it from 1, then this is the probability of an error, at least one. So in order to determine this probability of no errors, what I'm going to do is multiply the individual probabilities of no error for feature I. Now, what does that really mean? Well, let's go back to our distributions. For the type 2 error, we're talking about no error corresponding to the region under the curve here So we're looking at this probability, and we're saying this is the probability of no error. And we would have to do that for type 1 as well. Now I'm multiplying this for each feature because essentially we're saying that the features don't affect each other. In other words, they're independent. So here's an example. If we assume that the probability of an error for feature I is 0.0001, then the probability of no error would be 1 minus 0.0001 for one feature. And then I'm going to raise that to the number of features n to give me this probability of no error. If I do that, I get this type of plot, which looks fairly linear because, again, we're dealing with very small values here. But you can see after a reasonably small number of features, in this case 15, I do have a significant probability of encountering an error, and that could be either a type 1 or type 2 error. So we've got 16 out of 10,000 parts that are going to have an error just due to the gauging itself. So when we think about gauge error, we have to think about the fact that our process introduces variation based on the process capability, and that our type 1 and type 2 error are based upon the gauge dimensions. And then each time we check an individual part feature, it's possible that it's compounded because we can have multiple errors occurring. Error in gauges can contribute to your manufacturing costs, type 1, and functionality problems, type 2. We saw with the gauge dimensions that type 2 errors are less likely than type 1 errors, which is a good thing. And also, based on the cumulative errors, those potential errors can add up. And so the more features you have, the more likely that you encounter either a type 1 or type 2 error.